Welcome to this walkthrough of LeetCode problem number 1705, maximum number of eaten apples. In this problem, we'll explore an efficient strategy to maximize the number of apples eaten before they rot. Let's dive in and break this challenge into manageable steps. In this problem, we are tasked with maximizing the number of apples we can eat under certain conditions. We are given two arrays, apples and days. The apples array tells us how many apples grow on each day, while the days array specifies how many days those apples will last before they rot. For example, if apples I is 3 and days I is 2, it means 3 apples grow on the ith day, and they will spoil after 2 days, starting from that day. The challenge is that we can eat at most 1 apple per day, and only if there are non-rotten apples available. The goal is to write a function that calculates the maximum number of apples we can eat, considering these constraints. The input size can be quite large, so the solution needs to be efficient. Let's now break this down further with examples. Let's look at an example where apples equals 1, 2, 3, 5, 2, and days equals 3, 2, 1, 4, 2. Here, on day 0, we have 1 apple that will last for 3 days. On day 1, we get 2 apples that will last for 2 days, and so on. To maximize the number of apples eaten, we eat 1 apple each day from the available non-rotten apples. For instance, on day 0, we eat 1 apple from the first batch, and on day 1, we eat 1 apple from the second batch. On day 2, we eat another apple from the second batch since it hasn't rotted yet. We continue this process, prioritizing apples that will rot sooner. By the end, we've eaten a total of 7 apples, which is the output. Continuing the example, on day 3, we eat an apple from the fourth batch, which initially had 5 apples and a 4-day expiration. On day 4, we eat another apple from the same batch, leaving 3 apples with 3 days left before they rot. Similarly, on day 5, we eat another apple from this batch, and on day 6, we eat the last apple before it rots. The total number of apples eaten is 7. This demonstrates how we need to prioritize apples with shorter lifespans while ensuring we eat the maximum possible number each day. Now, consider another example where apples equals 3, 0, 0, 0, 0, 2, and days equals 3, 0, 0, 0, 0, 2. On day 0, 3 apples grow, and they will last for 3 days. On subsequent days, no new apples grow until day 5, when 2 apples are available that will last for 2 days. To maximize the number of apples eaten, we eat 1 apple each on days 0, 1, and 2 from the first batch. Then on day 5, we eat 1 apple from the 6th batch, and on day 6, we eat the last apple from that batch. The total apples eaten in this case is 5, as shown in the output. Finally, let's examine a case where no apples are available. With apples equals 0, 0, 0, 0, 0, and days equals 0, 0, 0, 0, 0, there are no apples to eat on any day, so the output is 0. This example highlights edge cases where the input arrays contain zeros. Additionally, the constraints remind us to handle large inputs efficiently, as both arrays can have up to 20,000 elements. Situations where apples expire quickly or last for many days also require careful prioritization. For instance, apples with shorter lifespans should be eaten first to avoid wastage. With these considerations in mind, the problem tests our ability to design an optimal solution that balances efficiency and correctness. To tackle the problem of maximizing the number of apples eaten before they rot, we considered 2 main approaches. The first is the brute force approach. Here, the idea is simple: each day, you check all apples available to see which ones are still valid, meaning they haven't expired, and then eat one of those apples. To do this, we maintain a list of apples and their expiration dates, updating it daily to remove expired apples. However, while this approach is intuitive, it's computationally expensive. Each day, we have to traverse the list of apples to find valid ones, leading to a time complexity of n squared for n days. This makes it impractical for larger inputs. The alternative is an optimized approach using a min heap. The intuition here is to use the heap to manage apples by their expiration dates efficiently. Each day, we add apples and their expiration dates to the heap. The heap structure allows us to prioritize apples with the earliest expiration, ensuring they are eaten first to avoid wastage. It also facilitates the removal of expired apples quickly. This approach, leveraging the heap, is far more efficient and avoids the repeated traversal that hinders the brute force method. The optimized approach using a min heap has a significant advantage in terms of complexity. Operations like inserting and removing elements in the heap are performed in O log n time, and since we perform these operations for n days, the overall time complexity becomes O n log n. This is a significant improvement compared to the O n squared complexity of the brute force approach. Additionally, the heap method is scalable, meaning it handles larger inputs effectively. Its efficiency stems from the fact that it tracks expiration dates dynamically, reducing unnecessary checks. Another benefit is its simplicity of implementation, as heap operations are straightforward to code and maintain. Considering these factors, the min-heap approach clearly stands out as the preferred strategy. On the other hand, the brute force method, while conceptually simple, is computationally prohibitive for larger datasets. It fails to utilize the structure of the problem, such as prioritizing apples by expiration, making it less practical. With the min-heap approach, there are some trade-offs to consider. While it is highly efficient in terms of time complexity, achieving O n log n, it requires additional space to store the heap, leading to an O n space complexity. However, this trade-off is reasonable because the speed-up gained in time complexity far outweighs the extra memory usage. The heap approach successfully balances these factors, offering an optimal solution for the problem. It efficiently manages the expiration dates of apples, ensures minimal wastage, and remains straightforward to implement. This combination of speed, clarity, and scalability makes it the best choice compared to the brute force method, which is both time-consuming and inefficient for larger inputs. Ultimately, the heap-based solution demonstrates how leveraging data structures effectively can significantly enhance problem-solving efficiency. In this problem, we aim to maximize the number of apples eaten before they rot. Each day, a certain number of apples become available, and each batch comes with an expiration period specifying how long those apples stay fresh. The key challenge is to determine the maximum number of apples that can be consumed, given the constraint of eating only one apple per day. To solve this, we use a greedy approach combined with a priority queue, also known as a min-heap. This data structure helps us efficiently track which apples will expire the soonest, ensuring that no edible apples are wasted. To start, we initialize our data structures, a min-heap to store tuples of expiration dates and the number of apples available for each day, and a counter called eaten_count to keep track of the total number of apples consumed throughout the process. These two components form the foundation of our algorithm, allowing us to systematically decide which apples to prioritize each day. For the main part of the algorithm, we iterate day by day. On each day, the first step is to remove any rotten apples from the heap. These are apples whose expiration dates are less than or equal to the current day. Next, if new apples are available that day, we calculate their expiration date by adding the shelf life to the current day and push this information as a tuple into the heap. Once the heap is updated, we check if there are any apples that can be consumed. If the heap is not empty, we pop the batch of apples with the nearest expiration date, eat one apple from that batch, and reduce its count. If there are still apples remaining in that batch, we push the updated entry back into the heap. Finally, we increment our eaten_count to reflect the apple consumed that day. After processing all the given days, we handle any remaining apples left in the heap. This involves continuing to eat one apple per day until the heap is empty or all apples have rotten. The result, stored in eaten_count, gives us the maximum number of apples we managed to eat. This greedy approach is effective because it ensures apples are consumed in the order that minimizes wastage. By always prioritizing apples with the nearest expiration date, we avoid letting edible apples rot unnecessarily. The use of a min-heap is crucial here, as it allows us to efficiently retrieve and manage the apple batch with the earliest expiration date. Each operation, such as adding a new batch or removing rotten apples, is performed in O log k time, where k represents the number of batches in the heap. The algorithm also handles edge cases seamlessly. For instance, on days when no apples are available, no entries are added to the heap. Expired apples are automatically removed during the daily cleanup step, and the algorithm continues past the initial end days if there are still apples remaining in the heap. The two main data structures used are the min-heap, which stores the expiry_date, apples, pears, and counters for tracking the current day and total apples eaten. Together, these components provide an efficient and robust solution to the problem. Analyzing the complexity of this algorithm, the time complexity is O, n plus k log k. Here, n represents the number of days in the input, and k is the total number of apple batches added to the heap. Each batch is added to or updated in the heap at most once, and each heap operation takes O log k time. The space complexity is O, k, as the heap stores up to k unique, expiry_date, apples, pairs at any given point. To further optimize, we can implement early termination. If the heap becomes empty before the simulation ends, we can stop processing since no apples are left to consume. Additionally, heap updates are performed only when absolutely necessary, either when apples are eaten or when new apples are added, minimizing unnecessary operations. These optimizations ensure that the algorithm remains both time efficient and space efficient, making it well suited for handling large inputs. This solution to LeetCode problem number 1705, maximum number of eaten apples, is designed to efficiently track available apples and their expiration days using a min-heap priority queue. The goal is to maximize the apples eaten, ensuring that no more than one apple is consumed per day and expired apples are discarded. We start by importing Heap to use Python's Heap implementation. The eaten apples function initializes max_apples to count eaten apples, min_heap to store tuples of expiration day and available apples, and iterates through all days using a variable day. For each day, we first check if new apples are available, apples, day 0. If so, we push their expiration day, day plus days, day, and count into the heap. This ensures that apples are organized by their earliest expiry. Next, we clean the heap by removing entries where apples are already rotten, expiration day equals current day, or exhausted, available apples equals 0. This step ensures that the heap only holds valid apples. If the heap is not empty, we pop the earliest expiring apples and consume one of them. If there are more apples remaining, we push the updated count and expiration day back into the heap. Finally, the loop continues for all days in apples plus additional days to consume any remaining apples in the heap. The function returns max_apples, the total number of apples eaten. This approach is efficient due to the heap operations, which take logarithmic time. The algorithm processes each apple addition and removal in O log n, where n is the number of days. Since the loop runs for the length of apples plus the time to consume leftovers, the overall complexity is well suited for inputs up to 10 to the power of 4 elements. Here, we begin by importing the necessary Java utilities, including the priority queue class. The method eatenApples takes two arrays as input, apples, which indicates how many apples are available each day, and days, which specifies how many days these apples will last. We initialize maxApples to keep track of the total number of apples eaten and create a min-heap priority queue to manage the apples, where each entry is an array containing the expiry day and the remaining count of apples. The priority queue is sorted based on the expiry day, ensuring that the apples expiring soonest are prioritized. Inside the while loop, the algorithm continues as long as there are more days or apples remaining in the heap. On each day, we first check if new apples are available. If so, we calculate their expiry day and add them to the heap. Next, we clean up the heap by removing apples that have either expired or been completely consumed, ensuring only valid entries remain in the queue. Finally, if any apples are still available in the heap, we eat one, decrement its count, and reinsert the entry if it still has apples left. After consuming an apple, we increment the day variable to move to the next day in the simulation. This process ensures that we evaluate each day's available apples and manage the heap efficiently. Once all days have been processed and the heap is empty, the loop terminates. At the end of the method, we return the value of maxApples, which represents the maximum number of apples that could be eaten under the given constraints. This implementation efficiently handles the problem by leveraging a min-heap to prioritize apples based on their expiry, ensuring that we always consume the apples that are nearest to expiring first. The result is a solution that balances simplicity and computational efficiency while adhering to the problem's requirements. Here, we're starting with a basic example where the expiration days for the apples do not overlap. On day 0, we get 3 apples that will expire on day 3. These are added to the min-heap as the pair, 3, 3, where the first value is the expiration day and the second is the count of apples. We eat 1 apple, reducing the count to 2, and update the heap to reflect this as 3, 2. The total apples eaten so far is 1. On day 1, no new apples arrive, but we can eat one from the heap. This leaves one apple with an expiration day of 3, and the heap now reflects this as 3, 1. The total apples eaten increases to 2. On day 2, there are still no new apples arriving, but we eat the last remaining apple from the heap. After eating, the heap becomes empty because there are no apples left. The total count of apples eaten is now 3. By day 3, no apples are available to eat, so the process stops. The final count of apples eaten in this example is 3. In this example, we introduce overlapping expiration days. On day 0, we receive one apple that expires on day 3. This is added to the heap as 3, 1. After eating, no apples remain, so this entry is removed from the heap, leaving it empty. The total apples eaten is 1. On day 1, 2 new apples arrive with an expiration of day 3. These are added as 3, 2. We eat one apple, leaving one in the heap, which is updated to 3, 1. The total apples eaten becomes 2. On day 2, 3 new apples arrive, also expiring on day 3. These are added to the heap as 3, 3. Since the earlier batch of apples with expiration day 3 has only one left, this is removed from the heap. After eating one apple, 2 remain from the new batch, updating the heap to 3, 2. The total apples eaten is now 3. On day 3, 5 apples arrive with an expiration of day 7. These are added as 7, 5. The earlier batch of apples, expiring on day 3, is removed. After eating one apple, 4 remain in the heap, updated as 7, 4. The total increases to 4. On day 4, 2 more apples arrive with an expiration of day 6. These are added as 6, 2. After eating one apple, 1 remains from this batch, and the heap becomes 6, 1, 7, 4. The total eaten now reaches 5. By the end of this example, the final output is 5 apples eaten. In the next scenario, we encounter a situation where some apples rot before they can be eaten. On day 0, we receive one apple that expires on day 1. It is added to the heap as 1, 1. After eating, no apples remain, and the heap becomes empty. The total apples eaten is 1. On day 1, no apples arrive, and since none are available, no eating occurs. On day 2, 1 new apple arrives with an expiration of day 3. This is added to the heap as 3, 1. After eating, no apples remain in the heap, which becomes empty again. The total apples eaten increases to 2. By day 3, no apples are available to eat, so the process stops. The final count of apples eaten in this example is 2. In this problem, we analyze the time complexity by focusing on the operations performed during the iteration over days. First, each day we check if new apples are available. If they are, we add them to a min heap using the heap.heapPush operation. This operation ensures the heap remains sorted and is performed in O log k time, where k is the current size of the heap. Over all days, the worst-case scenario is when each day adds a new entry to the heap, leading to a total time complexity of O n asterisk log k. Since the heap size is bounded by the total number of days n, we can replace k with n, resulting in this step contributing O n asterisk log n time. Next, we also remove expired or consumed apples from the heap using heap.heapPop. Each heap pop operation is similarly O log k, and in the worst case, we perform one such operation per day, leading to an additional O n asterisk log n for this step as well. Eating an apple involves checking if the heap is not empty, removing the top element with heap pop, and possibly reinserting an updated entry if there are apples remaining. Each of these operations is also O log k, and since this happens at most once per day, it contributes another O n asterisk log n in the worst case. When we combine all these operations, adding apples, removing rotten ones, and eating apples, the dominant term remains O n asterisk log n. Therefore, the overall time complexity of the algorithm is O n asterisk log n. Shifting to space complexity, the primary contributor is the min heap, which stores tuples of expiration days and the number of remaining apples. In the worst case, the heap may store up to n tuples, one for each day, where each tuple takes O(1) space. Hence, the space complexity for heap storage is O n. Beyond the heap, the algorithm uses a few additional variables such as max_apples to track the total apples eaten, day to iterate through the days, and other loop iterators. These variables occupy constant space, contributing O(1) to the overall space complexity. When we combine the heap storage and the space used by these variables, the total space complexity is O(n). Now, let's consider the best, average, and worst case scenarios. In the best case, if all apples have the same expiration day or only a few apples are available, the heap remains small, and the logarithmic operations on the heap are minimized. This reduces the time complexity to approximately O(n). Typically, in the average case, apples have varying expiration days, leading to a moderately sized heap. Here, the time complexity is O(n*log n). In the worst case, every apple has a distinct expiration day, and none are eaten early. This causes the heap to grow to its maximum size of n, and the time complexity remains at O(n*log n). The space complexity in this scenario is also at its maximum, O(n), due to the heap size. Comparing this to a brute force or naive approach highlights why the heap-based solution is more efficient. A naive method would involve scanning the entire list of apples each day to determine which ones can be eaten. This would result in a time complexity of O(n²), as for each day, we iterate over the entire list. In contrast, the heap-based solution efficiently manages expiration days and valid apples, reducing the time complexity to O(n*log n, while keeping space usage reasonable. Finally, let's solidify our understanding of the algorithm's big O notation. Each heap operation, whether it's a heap push or heap pop, has a time complexity of O log k, where k is the heap size at that moment. Over the course of the algorithm, these operations are performed up to n times, resulting in a total cost of O(n*log n). Other aspects of the algorithm, such as updating variables or checking conditions, are constant time operations and do not influence the overall complexity. Therefore, the dominant term remains the heap operations, giving the algorithm a final time complexity of O(n*log n). As for space, the heap size grows at most to n, leading to a space complexity of O(n). This efficient use of time and space makes the heap-based solution significantly better than a brute force approach for solving the problem. Let's start by discussing some common mistakes people make when solving this problem. First, ignoring expiration dates is a frequent issue. If you consume apples without considering their expiration, you might end up wasting apples that should have been eaten earlier. The correct strategy is to always prioritize apples with the nearest expiration dates to minimize waste. Next, choosing the wrong data structure can also lead to inefficiencies. If you use a list or an array to track apples and their expiration dates, sorting and prioritizing becomes cumbersome, which increases the time complexity. Instead, a min-heap or priority queue is the right choice because it allows you to efficiently retrieve and remove the apples with the nearest expiration. Another common pitfall is not handling edge cases properly, such as days with 0 apples or when all the apples in the heap have expired. These scenarios can lead to runtime errors or incorrect results, so it's important to explicitly account for these cases in your solution. Another mistake to be mindful of is overcomplicating the solution. Sometimes, people introduce unnecessarily complex data structures or algorithms, which can increase implementation time and make the code more prone to bugs. The best approach here is to stick to a simple greedy strategy combined with a min-heap for optimal efficiency. Additionally, you may encounter issues with incorrect heap updates. If you forget to remove expired apples from the heap before trying to consume them, you could end up using apples that are already spoiled. To avoid this, make sure you remove all entries from the heap where the expiration date is less than or equal to the current day before consuming any apples. This ensures that you are always working with valid data and prevents logical errors. This problem also provides valuable insights for interviews. It's a great example of how a greedy algorithm can be combined with a priority queue to optimize decision-making. Interviewers often look for your ability to choose the right data structure to solve such problems efficiently. A key focus here is minimizing waste, such as expired apples, while maximizing the number of apples consumed. You should be able to explain the trade-offs between a greedy approach and a brute force method during your interview. It's also important to discuss edge cases, like days with 0 apples, situations where all apples expire on the same day, or scenarios involving very long expiration periods. Additionally, interviewers might challenge you with follow-up questions, such as introducing constraints like a daily limit on the number of apples you can eat or handling multiple types of fruit. You can also connect this problem to other related ones, such as task scheduler, meeting rooms 2, queue reconstruction by height, or maximum number of events that can be attended. All of these problems share similar concepts of using greedy algorithms and priority queues to optimize outcomes. Now, let's explore some alternative approaches to solving this problem. The brute force approach involves iterating through all days and attempting to consume apples without prioritizing their expiration. While this approach is simple to implement, it is highly inefficient with a time complexity of n squared. Another option is a greedy approach combined with sorting. Here, you sort all apples by their expiration dates and then iterate through the sorted list to consume them. This method has a better time complexity of n log n due to the sorting step, but it may not perform well in dynamic scenarios where new apples are added each day. The most efficient solution, and the one we recommend, is the optimal greedy approach using a min heap. This method dynamically tracks and removes apples with the nearest expiration dates, ensuring that you always consume the most perishable apples first. It offers a time complexity of n log n, and handles dynamic input effectively, making it the best choice for this problem. Great job making it to the end. To summarize, we used a priority queue to track apple expiration dates efficiently, ensuring we maximized the number of apples eaten before they spoiled. Remember the importance of edge cases and the versatility of heaps for deadline-based problems. Thanks for watching, and be sure to like and subscribe for more tutorials. Keep coding and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!